So for this week, we're talking about hypothesis testing. This is the next logical step from the confidence intervals that we talked about last week. When we look at hypothesis testing, we take samples, again, trying to make a conclusion about our population. But we can't just let the value of the sample, it's kind of the difference between a point estimate and the interval estimates from last week. Just because the sample gives us a value that is either smaller or larger than what we're looking for, doesn't mean we can say the population is there. We have that margin of error, like in the confidence intervals. And so the hypothesis testing process is a way of accounting for that margin of error. So some examples: sharing prescription drugs with others can be dangerous. Is this a common occurrence among teens? We could do a hypothesis test to find that out. Or the National Association of Colleges and Employers stated that the average starting salary for students graduating with a bachelor's degree in 2010 is $48,351. Is this true for your college? Again, you can set up a hypothesis test to test that. So how do we answer these questions using sample data? Since we don't have access to the whole population, how can we choose a sample in order to get a reasonable determination as to whether these statements are true or not? And so chapter 9, we use the point estimate and the interval estimates to estimate the population characteristics. Now we're going to look at how do we tie that into actually making a conclusion about those characteristics. So we're going to use hypotheses and hypothesis testing to decide whether a statement is plausible or not. So what is the test of hypothesis? So a test of hypotheses is a method that uses sample data to decide between two competing claims, these are our hypotheses, about the population characteristic. Now the key is those two competing claims have to be what we would refer to as all-inclusive or complements. They must contain all of the possible results. Either it's greater than this number or it's less than or equal to this number. It can't be, anything else. So is it one of the values of the sample statistic? So what we're looking at here is a bell curve. And this bell curve is based off of assumptions about the population. So we assume that the population has a certain characteristic, mainly that center, the mean or median. We usually state it as a mean. If that assumption is true, it's very likely that the sample will give us a sample statistic in that range, and very unlikely that it'll give us sample statistics in those ranges. And that's what hypothesis testing is determining what is this likely range and unlikely range. Then if we get something in one of those unlikely ranges, then we go to the alternatives. So we have, for hypothesis testing, we have two hypotheses that we have to state for each problem. One is the null hypothesis. It's denoted by H0. It is a claim about the population characteristic that is assumed to be true starting out the process. So if we had no other evidence, this is what we would assume to be true. Whether it's a previously established value or a previously made claim, it's generally what we refer to as the status quo. If we didn't do anything, this is what a majority of the population would still continue to believe. So it's the safe bet, in other words. So then the alternative hypothesis is, if the null hypothesis were not true, this has to be everything else. This is the competing claim. So this is telling us what the alternative is, or what would have to be true if the null hypothesis were not. Now this textbook uses HA, other textbooks use H1. They mean the same thing. They're just the alternative or the competing hypothesis with that null. So what we're usually trying to do is we're trying to determine if the claim in the alternative hypothesis is believable. So we do that by assuming that the complement or the opposite is true, and then to see if we can find significant evidence against the null. Generally, what we are testing is the null because we are setting up all of our characteristics based on the null being assumed to be true. So to determine what the null hypothesis should be, we have to look at the objectives of the problem that we're working on. The hypothesis statements are always about the population, never about the sample. So we're always talking about what the population is. Even though we're using sample information, hypotheses are about sample. So the null hypothesis, like we said, is what's assumed to be true before we start. So in a court of law in a murder trial, the defendant is innocent. We assume they are innocent until proven guilty. The alternative hypothesis would be what has to be true if the null is false. So if there's strong evidence that seems to refute the null hypothesis or reject that null hypothesis, the alternative is what has to be true. So in this case, the defendant would be guilty. So what we're looking at here, remember that in the court of law, it's beyond reasonable doubt. So we're looking for strong evidence beyond a reasonable doubt that null hypothesis is faulty. So therefore we can reject it and move on to the alternative hypothesis. If we do not have convincing evidence, then we fail to reject the null hypothesis. Now remember, the verdict is not guilty or innocent, it is guilty or not guilty. Either they found enough evidence to reject their innocence and take their guilt, or we did not find enough evidence to reject their guilt. We failed to find them guilty. We did not find them innocent. We're never, ever proving the null. We are either just finding evidence, strong evidence against it, or failing to find strong evidence against it. But when we don't reject it, we are not putting evidence in favor of the null. We're just saying we don't have strong enough evidence against it yet. So either we can reject the null or fail to reject the null. Like I said, we never accept the null or prove the null. We just fail to reject it. So our null hypothesis is usually that the population characteristic equals hypothesized value. Now the null hypothesis is always equal. Even though we don't necessarily always mean equal, we write it as equal. The reason for that is that's the value we're going to use to construct that bell curve that is our theorized, our hypothesized population bell curve, and then place our sample data on that curve to see whether that null hypothesis is reasonable, or see if that sample result is reasonable based on that null assumption. So the null hypothesis is always equal. The alternative has three choices. The alternative can be greater than, like that. So notice it's the same population characteristic that we're using, and it's the same hypothesized value that we're using. In this case, it's greater than. That's what we refer to as a one-tail and right tail or upper tail test, because we'd reject on one tail of that, and it would be this upper tail up here, the right tail. So if we get our sample gives us a value out there, that's where we're going to reject. It could be less than. That's also a one tail, but that would be a left tail test. Because in that case, if we get data values down in here, we would reject. And then the third possibility is not equal to. That's a two-tailed test, because we would reject if we're too small or if we're too large with our sample statistic. So again, those first ones are considered one-tailed tests. And the third one is a two-tailed test, because we can reject in both directions. So let's practice writing the hypotheses first. That's one of the more difficult things to do. So sharing prescription drugs with others can be dangerous. A survey of representative sample of 592 U.S. teens ages 12 to 17 report that 118 of those surveyed admitted to having shared a prescription drug with a friend. Is this sufficient evidence to say that more than 10% of teens have shared prescription medications? So we're trying, it says, is this sufficient evidence that this is true? So that is always the alternative, what we're trying to find sufficient evidence for. So the alternative, HA, would be that proportion is greater than 10%. The null then is the neutral statement. So in this case, the proportion P of teens is our population of interest, the portion of teens who have shared medications. The hypothesized value is 10%, so that's going to go in our null hypothesis. And this indicates the direction of our alternative. It says more than 10%. That's where we got that greater than 0.10 down there. I'm going to get that out of the way because the PowerPoint is going to put those hypotheses in for us. So, oops, it did not put them in for us. There they are. Skip past them and double clicked. So the null is that the proportion equals 0.1 or 10%. The alternative then is that the proportion is actually greater than 10%. Now, technically, the null here is saying that really they think it's less than or equal to 10%, but they always word it as equal, remember, because we use the equal to that value to construct that bell curve. Compact fluorescent light bulbs are much more energy efficient than regular incandescent. EcoBrand 60-watt CFL bulbs state on the package an average of 8,000 hours. People who purchase this brand would be unhappy if the bulbs lasted less than 8,000 hours. Sample of these bulbs will be selected and tested. So again, the claim is that they last 8,000 hours. People would be unhappy if they lasted less. So our alternative would be the mean is less than 8,000 hours. And so then the null, the neutral, is that mean has to be equal to 8,000. Now remember, this really does include equal to or greater than 8,000, but we're just saying equal to because that's how we construct the null hypothesis. So the character of interest here is the mean life of those light bulbs. The hypothesized value is 8,000 hours. And again, that is telling us that the alternative would be less than, because that's where people would be unhappy if we found that to be true. So because in variation of manufacturing process, tennis balls produced by a particular machine do not have the same diameters, suppose the machine was initially calibrated to achieve the specification of a mean of 3 inches. However, the manager is now concerned that the diameters no longer conform to this specification. The mean diameter is not 3 inches, production will have to be halted. So here again, their population of interest is the mean diameter of the balls. We're looking at what words indicate the direction of the alternative. Well, here, if they're too small or too large, that's going to be a problem. So the alternative would be not equal. So there we go. The alternative is not equal to 3 inches. The null is that they are equal to 3 inches. Nothing's wrong, in other words. So for each pair of hypotheses, indicate which are not legitimate and explain why. So up here, first one, there's an equal sign here in the alternative. That is not legitimate. Should only be greater than in the alternative. This one, this is an X bar. That's a sample statistic, not a population parameter. Here, let's see. That one looks like it's legitimate because P is a population proportion. We have the same hypothesized value, and this is equal to, this is not equal to. That one should be good, and it is. Next, this one's very subtle. It's a population proportion. It's equal to and greater than, but this is 2.3 and this is 3.2. Those two values have to be the same. The equal to has to be the null hypothesis, so that one cannot be legitimate hypotheses. So when you perform a hypothesis test to make a decision, you either reject HO or you fail to reject. We don't ever prove HO, we just fail to reject it. So when you make one of these decisions, there's a possibility that you could be wrong. And so there's two different types of errors that can be made. So the first type of error, called the type 1 error, is the probability that you reject the null hypothesis even though it's actually true, which means you just got a bad sample or an unusual sample that led you to that conclusion. Type 1 error, the probability is called alpha. This is the Greek small letter alpha. That is called the level of significance of a test. That is the probability of doing everything correctly and still rejecting the null hypothesis even though it's true. So it's the chance that you're taking. It's basically it's your risk tolerance. It's your risk of rejecting the null hypothesis even though it's true. Remember, the null hypothesis is the safe statement. We don't want to move away from the null unless there's strong evidence saying that there's something better. The type 2 error then is the error of failing to reject the null hypothesis even though it's false. The probability of this is called beta. That little b is the Greek symbol for the small beta. This is not easy to quantify. It's pretty advanced statistical techniques beyond the scope of this course to quantify that. So here's just the table. If the null hypothesis is true and we fail to reject, that is a correct result. If it is true and we reject it, that is a type 1 error. If the null hypothesis is false and we reject it, that is a correct result. If it is false and we fail to reject it, that is a type 2 error. So the U.S. Bureau of Transportation Statistics reports for 2009, 72% of all domestic passenger flights arrived on time, meaning within 15 minutes of its scheduled arrival time. Suppose that an airline with a poor on-time record decides to offer its employees a bonus if, in an upcoming month, the airline's proportion of on-time flights exceeds the overall 2009 industry rate of 0.72 or 72%. So the null hypothesis, the bureau here, or the company, is trying to get the rate above 0.72. So the alternative would be the proportion is greater than 0.72. The null hypothesis, of course, is always equal to, but again, we know it really means equal to or less than, but we're saying equal to because that's what we're basing our test on. So a type 1 error would be rejecting that, saying that the proportion is better than 72 when it really isn't. Type 2 error would be failing to reject it, even though the proportion is better than 72% or 0.72. So the employees didn't get the bonus, even though they had earned it. In 2004, Vertex Pharmaceuticals, a biotechnology company, issued a press release announcing that it had filed an application with the FDA to begin clinical trials on an experimental drug, VX-680, that had been found to reduce the growth rate of pancreatic and colon cancer tumors in animal studies. So, data resulting from the planned clinical trials can be used to test. Let mu equal the true mean growth rate for the tumors in the patients. So HO means the mean growth rate of the tumors for patients is not for patients who would not take the experimental drug. So we're making that assumption that that's the mean growth rate. We might have that from historical data, that would be the growth rate for patients not taking this current drug. And then the alternative would be that the growth rate is going to be less than that historical rate for patients not taking this drug. So a type 1 error would be rejecting HO even though it's true, even though the rate is at or above the mean growth rate for other patients, we would still reject it, claiming that it's smaller. So we would claim the drug is more effective even though it isn't. Potential risk is we replace the old drug with a new drug even though the new drug is not more effective. So we're replacing with a drug that's less effective. Type 2 error would be failing to reject it even though the new drug is better. So the consequence here is we have a drug that could be more effective, but we're not using it because we failed to reject the null here. So that new drug does not get used. So in an ideal testing situation, alpha and beta, the probabilities of the type 1 and type 2 errors would be 0. That's not possible to achieve. In fact, there's a balance. The bigger alpha becomes, the smaller beta becomes. Or the smaller we make alpha, the larger beta has to become in order to balance out. Now, there's not a set total form or anything like that, but that relationship exists. So usually we can control alpha. We can select the level of alpha. So normally we select the alpha to be the largest value we can tolerate for it, and then we just let beta fall where it comes. Typical value of alpha is level of significance of 0.05. That's 5%, or saying that 5 times out of 100, if we conducted this process correctly, we would reject HO even though it's true. So why don't we always choose a really small value of alpha? Because when we choose small, make alpha smaller, beta becomes larger. This goes through that relationship. So that's that alpha, that's that probability or chance of getting a type 1 error. So if that is true, then the curve really should be larger. It should be shifted to the right. So if we shift the curve, this area that's left over here, that's the probability of beta, the chance of beta, the type 2 error. But notice there, beta is relatively small. If we made alpha smaller and we shifted the curve, notice now beta is a lot larger. So the smaller we make alpha, the less chance we have of making a type 1 error. The larger we make beta, the greater chance there is of a type 2 error. So how do you decide what alpha should be used? So we look at it and we decide what is the maximum acceptable value, rather than the smallest, but what is the maximum accepted tolerance for risk here of making that type 1 error. So remember, if we choose too small of an alpha, or smaller than necessary alpha, we increase the size of beta. So the EPA has adopted what is known as lead and copper rules, which defines drinking water as unsafe if the concentration of lead is 15 parts per billion or greater, or if the concentration of copper is 1.3 parts per billion or greater. So here, obviously, our hypotheses for lead is the alternative. We want it to be less, so it's going to be the mean is less than 15 parts per billion. The null is going to be equal to. Well, we want to be very, very sure that it is less than 15 parts per billion. We don't want to conclude that it's less unless we are absolutely sure. This is going to be a very small alpha value, because a type 1 error would mean we drink this water even though it isn't safe. So we want alpha to be very, very small, since that type 1 error is a huge risk, has very bad consequences if we allow it to happen. Type 2 error is we conclude the water's bad even though it probably is safe. Well, this isn't a bad thing, because we're going to look for a safer source of water. It costs us extra money, but it doesn't affect our health, doesn't hurt our health. So the type 2 error is not that dangerous. It's not that huge of a deal. You'll lose a good water source, but you're getting a safer one. Again, it's just costing more money is really the consequence there. So the type 1 error is definitely the more serious consequence here. So we want alpha to be very small. So we might choose alpha to be 0.01. Let's look at this actual hypothesis testing process. There are two types of tests we're going to look at. Actually, two categories. There's a couple different types under each of them. We're going to look at the test for a population proportion. That's going to be the first one here. Then there's going to be a test for a population mean, and that's going to be divided into two possibilities. If we know the standard deviation, so we know the population standard deviation, or we don't know the population standard deviation. We're going to start off with the proportion. So the fundamental idea is we only reject HO if we observe sample results that were highly unlikely based on the assumption that HO was true. So we assume things to remember that we're looking at our sampling distributions, or if we take a sample and we calculate the proportion of the sample, we know the mean of those sample proportions is equal to the population proportion, and the standard deviation or standard error of those population proportions is the square root of the population proportion times 1 minus p over n. If we don't know p, the population proportion, we'll use the hypothesized value, or we can use a sample value. When n is large, the sampling distribution of p hat is approximately normal. So n has to be large enough to remember so that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So that means we're basically looking at that standardized value for our sample proportion or sample result. So in June of 2006, an Associated Press survey was conducted to investigate how people use the nutritional information provided on food packages. Interviews were conducted of 1,003 randomly selected adult Americans. Each participant was asked a series of questions, including the following two. Question 1, when you purchase packaged food, how often do you check the nutrition label? And 2, how often do you purchase food that is bad for you even after you check the nutrition label? It was reported that 582 out of that 1,003 responded frequently to the question about reading the nutrition label. Another 441 responded very often or somewhat often to the question about purchasing bad foods even after checking the label. So based on this data, is it reasonable to conclude that a majority of Americans frequently check nutrition labels when purchasing packaged food? The key word there is majority. Majority means more than 50%, more than 0.5. So there's our alternatives. That proportion is more than 0.5, so the null is the proportion equals 0.5. P is the true proportion of adults who frequently check the nutrition labels when buying packaged food. So there's our hypotheses. For this sample, the sample proportion, 582 out of 1,003 said yes, so that's a 0.58 sample proportion. Now that's bigger than 0.5, but remember there's a chance that we just had a skewed sample. Remember there's variation in that sample. If this is the curve, and if 0.5 is the true population proportion, we would accept those sample proportions to vary along that bell curve. So there's a chance, we don't know exactly where 0.58 lies in there right now, but there's a chance that we could get a population or sample proportion that's larger than 0.58, even though it really is 0.5. So we have to create a test statistic. So that's p hat minus p. So remember, p is the 0.5. That's the hypothesized proportion from the null hypothesis. So we're going to use those values, 0.5 for p and 0.58 for p hat. So 0.58 minus 0.5 divided by 0.5 times 0.5 over 1,003 square rooted gives us a test statistic of 5.08. So what this is telling us is where we really lie on this curve. So this is still the bell curve, and the center of that is still the hypothesized value of a proportion of 0.5 or 50%. But we're standardizing it. Remember, when we standardize a curve, the center or the mean becomes 0 and the standard deviation becomes 1. Well, 5.08 means we're way over here at 5.08 standard deviations above the mean. So now we need to find something called a p-value. The p-value is the probability of being further from the hypothesized value, or getting a more unusual value than this based on that the null hypothesis being true. Now the p-value, the way we calculate the p-value depends on the alternative hypothesis here. So our alternative hypothesis is greater than. So we want the probability of being greater than our test statistic. So 5.08 is way up here. Remember, this is 0, 1, 2, 3, 4, 5. Since this is greater than, we want the probability of being greater than that. Well, we find the probability of being greater than 5.08 with a mean of 0. This is normal, by the way. Normal CDF. Probability of being greater than 5.08. So it's 5.08 to positive infinity with a mean of 0 and standard deviation of 1. Well, the calculator is going to come back with something in scientific notation. It's basically saying 0. So since that probability is 0, it is very, very, very unlikely to get a worse result than that, if that null hypothesis is true. It's a very, very, very small probability of having a sample give us a worse result than that. So that is saying, since the p-value is small, we would reject the null hypothesis and say that there is convincing evidence to suggest that a majority of Americans, more than half, do check the nutritional label for buying food. So again, calculating the p-value I mentioned depends on the form of the alternative hypothesis. If it's greater than, we're finding the probability of getting z greater than our test statistic. Like that. If the hypothesis is, so that's the upper tail area above whatever our z-score is. If it's less than, then it's the probability of getting a z-score less than our test statistic. So the probability of z being less than that value from our sample. If it is a two-tailed test, not equal to, well then it's a combination. It's the probability of getting a z-score less than that value that we got, or negative of that value, and the probability plus the probability of getting a z-score greater than that value, that test statistic. Now, luckily, these two probabilities are always the same, so it can always just be 2 times the probability. If z, the calculated z from the sample, is positive, it would be greater than. If the calculated z from the sample is negative, of course, it would be less than that value. But it's 2 times the probability of being further away from the center of that curve. Those two tails will always, it's the sum of those two tails will always have the same probability. So to decide whether or not to reject HO, we simply compare the p-value to alpha, our level of significance. If the p-value is less than alpha, we will reject. If the p-value is greater than alpha, we fail to reject. So, a summary here, the null hypothesis is always that p is equal to some hypothesized value. Our test statistic is that z-score for that sample statistic. The alternative hypothesis, whether it's less than, greater than, or not equal to, determines how we find our p-value. If it's greater than, it's the value to the right of z. If it's less than, it's the value to less than z. Remember, z is our test statistic. And if it's not equal to, it's 2 times the area to the right if it's a positive z, or if it's a negative z, it's 2 times the area to the left. So p hat is our sample proportion from a random sample. Another assumption that we have to make for this test to work is that n is sufficiently large. In other words, n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. And that the sample is done without replacement, and the sample size, the sample is either done with replacement, or if it's done without replacement, the sample size is no more than 10%. The no should be highlighted there as well. It is no more than 10% of the population. So the population is at least 10 times the size of our sample. So let's go through an example here. A report states that nationwide, 61% of high school graduates go on to attend a 2-year or 4-year college the year after graduation. Suppose a random sample of 1,500 high school students graduated in 2009 from a particular state estimated the proportion of high school graduates that attended college the year after graduation to be 58%. Can we reasonably conclude that the proportion of this state's high school graduates in 2009 who attended college the year after school is different from the national average? Now, it just says different from the national average. It doesn't say less, it doesn't say greater. In our problems that we're going to do in this course, we're going to be told what to use for alpha. So we're asked to use alpha of 0.01. So the null hypothesis, of course, is going to be that the proportion that go on is 0.61. And the alternative is going to be that it's going to be different from 0.61. Notice we did not say when we were talking about the null that it was less than that. We just wanted to say it shows it different. So from those hypotheses, we're going to find our test statistic. Our assumptions, of course, that the 1,500 students were a random sample. We see that 1,500 times 0.61 is definitely bigger than 10. 1,500 times 0.39 is also bigger than 10. And we're assuming the population size is at least 10 times larger than the sample size. So our test statistic, we have 0.58 minus 0.61 divided by our standard error there, or standard deviation of the proportions, the square root of 0.61 times 0.39, or 0.39 is just 1 minus 0.61 over 1,500, giving us a test statistic of a negative 2.38. Now, since that's negative, this is a two-tailed test, so we got both tails to find our p-value on. But since that's negative, it's going to be the probability of z being less than negative 2.38. And of course, we're going to multiply that times 2. So the probability of being to the left of that, that's this probability here of being less than negative 2.38 is 0.0087. But because this is a two-tailed test, it's not just less than, it's not equal to. We have to multiply that times 2, which gives us 0.0174. Now remember, we're always comparing that to alpha, and we had alpha of 0.01. Since that is not less than alpha, it's greater than alpha, we fail to reject HO. So there does not appear to be enough evidence to say that the proportion of high school students who graduated in that state and went on to a 2- or 4-year degree was significantly different from the national average. We failed to reject the null hypothesis, so the only type of error we could have made was a type 2. Remember, type 1 can only occur if we reject the null hypothesis. Another example, December 2009, a county-wide water conservation campaign was conducted in a particular county. In 2010, a random sample of 500 homes was selected, and water usage was recorded for each home in that sample. Suppose the sample results were that 222 households had reduced water consumption out of the 500 surveyed. County supervisors wanted to know if their data supports the claim that fewer than half the households in the county actually reduced their water consumption. So their claim is that fewer than half, so that's going to be the alternative. Less than half, or proportion of less than 0.5. So the null is always equal to 0.5 then. Where P is the proportion of households that actually reduce their water usage based on the campaign. P hat is going to be the 220 out of 500, or 0.44. Now that seems to be less than 0.5, but again, is it significantly less? Is it far enough down that we can say that this really is a thing? Or is it close enough that we can say it might have been just caused by random sampling errors? So we verify our assumptions. It is a random sample of households. 250, or n times p is greater than 10. I mean, n, 500 is n, p is 0.5, that's 250. 1 minus p is also 0.5, so that's also 250, so both of them are bigger than 10. And we're assuming, it's reasonable to assume that the county had more than 5,000 people in it. So that we're less than 10% of the whole population. So we need our test statistic. So 0.44 minus 0.5 divided by our standard error there gives a test statistic of a negative 2.68. So on our bell curve, the null or the alternative hypothesis is less than as well. So all we're looking for is the probability of being less than that negative 2.68. So we look that up in our z-curves, that probability is 0.0037. Now did we specify alpha? Alpha was 0.01. We are definitely less than alpha, so we reject HO. Now, since we rejected alpha, the only type of error we could have made was a type 1 error. That we rejected, sorry, reject alpha. We rejected the null hypothesis. So we could have made a type 1 error. We could have rejected it even though it really is true. But there's only a 1% chance, or a 0.01, alpha chance of making that type 1 error. So let's go back to this sample data and create a confidence interval based on this sample data. We mentioned this a little bit last week, that the confidence intervals and hypothesis tests are really tightly bound together. So we're making that assumption that the population proportion is 0.5. But our sample data gives us a proportion of 0.44. We wanted to be, if we're saying alpha of 0.01, we'd put that 0.01 on both ends. So it really comes down to a 98% confidence interval, because the confidence interval has to be out of the center of the curve. So whatever we clip off on one tail, even though it was only a one-tailed test, we have to clip the same off on the other tail. So our 98% confidence interval goes from 0.388 to 0.492. Notice that this is 0.5. That was our hypothesized value of the population proportion. That interval, 0.492, goes from here, 0.388, all the way down here. So we are saying that that is way less than 0.5. That interval does not even go up to 0.5. So it is not possible. We are 98% confident that the true population proportion is in this interval, which means we're 98% confident that it's not 0.5, because 0.5 is not in the interval. So that supports our conclusion that we rejected that null hypothesis. And those should give the same conclusion, by the way, every time. So the college attendance revisited. Let's compute a confidence interval for this problem. So the data that was given, again, is alpha of 0.01, so that goes to both sides. We're going to end up with a 90, oops, this should be a 90. Oh, this is already split because it's two-tail. So that 0.01 is already split to the two sides, so we don't have to double it. So it is going to be a 99% confidence interval. It goes from 0.547 to 0.613. Notice 0.610 is in the interval. So that means that based on that sample result, it is possible that our assumption was true, or it's not at least highly unlikely that it was untrue, because the interval based on the sample gives us that the true population proportion could be that 0.60 because it's in our interval. That supports that decision that we failed to reject. Well, let's look at tests for the population mean now. Some assumptions. The first assumption is that we're looking at a large sample hypothesis test for the population mean. X bar is the sample mean from a random sample drawn from that population. Sample size n is large, in other words, it is at least 30. And the population standard deviation is either known or unknown. Now, this is something some textbooks don't do anymore. Even if it's unknown, if the sample size is greater than 30, we can still use the same process, the Z process. If it's less than 30 and we don't know the population standard deviation, we have to use a T distribution or a T test. A lot of other textbooks have gone now. The reason we did this was because you have to have a separate table for every sample size for the T distribution. So in order to avoid that, if the sample gets larger than 30, the T distribution is really close to the Z distribution, the normal probability. So if you get above a sample size of 30, we just say, let's just go ahead and use a normal distribution and not worry about it because it's really close to the same. With technology now, though, you don't have to have the tables. The calculator does the work. So most textbooks don't use that large sample distinction anymore. They just say, if you know the population standard deviation, you use the Z-test. If you don't know it, you use the T-test. For this textbook, though, even if you don't know the population standard deviation, if the sample size is bigger than 30, you can still use the Z-test. There's our test statistic. Remember, this is that standard deviation of the sampling distribution. If it's a small sample and the population standard deviation is not known, we use that t-test. The difference is we have to use the sample standard deviation instead of the population standard deviation. And we have to know something called the degrees of freedom. DF stands for degrees of freedom. It is the sample size minus 1. So one sample t-test for population mean. So that's going to tell us that we do not have the population standard deviation given to us. You can see this is very similar to our P, test for proportion. The null hypothesis is always equal to. The alternative, if it's greater than, it's a right-tailed test. If it's less than, it's a left-tailed test. Of course, all we're adding in is degrees of freedom here for the t-distribution. If it's not equal to, then it's a two-tailed test. So X bar and S are the sample mean and sample standard deviation for a random sample. Population size N is larger than 30, or the population is at least approximately normal. So even if the population is not approximately normal, if the sample size is greater than 30, the sampling distribution is still approximately normal. So we can still use these methods. If the sample size is less than 30, we do have to know that the population is approximately normally distributed. So here's a study of Pennsylvania State University investigated whether time perception, an indication of a person's ability to concentrate, is impaired during nicotine withdrawal. So after a 24-hour smoking abstinence, 20 smokers were asked to estimate how much time had elapsed during a 45-second period. Researchers wanted to see if smoking abstinence had a negative impact on time perception, causing elapsed time to be overestimated. So they wanted to show it to be overestimated. So that says the alternative is going to be greater than a value. So suppose the resulting data on perceived elapsed time were as follows. So there is our data values. We have what, 1, 2, 3, 20 data values there. Since that is less than 30, we need to know that the population is approximately normally distributed. So we're going to find the mean and standard deviation for that sample. So they calculated them for us right there. State the hypotheses. So the null hypothesis is going to be that the mean was equal to 45. The alternative is they're saying more, they said more than back here, if you recall, that the absence had a negative impact on time, causing them to overestimate the time. So the alternative is going to be greater than 45. The mean is greater than 45. We have to verify our assumptions. First assumption, random sample. It's a representative random sample. Since the size was not at least 30, we must determine if it's possible that the population is approximately normal. One way to do that is to just plot the data values from our sample. Either a box plot or a dot plot works. This box plot is relatively symmetrical. It's skewed a little bit over here. I would say that this might be too skewed to use. It's on the edge. It's approximately symmetrical, so it's right there. If this tail here were a little bit longer, I'd maybe say we couldn't use it. Now, of course, this portion of the box is bigger than that portion. If that were switched, that would show an extreme skew to the left or lower tail. Then we probably wouldn't be able to use it. But it's on the edge, but that one is just close enough to use to say that this is close to normally distributed. So then we're going to compute our test statistics. So our mean of our sample, 59.3, minus the hypothesized value of 45, over, remember it's standard deviation divided by the square root of sample size, gives us 6.5. So that's giving us a value up here of a positive 6.5. We're way up here. Now, since the alternative hypothesis is greater than, we want the probability of being greater than 6.5. This is with 19 degrees of freedom. Remember, sample size is 20. 20 minus 1 equals 19. The p-value of that, just like it would be for a normal, being greater than a 6.5 would be extremely large. It's approximately 0. So since the p-value is less than alpha, we reject the null. So there's convincing evidence that people in nicotine withdrawal do overestimate time intervals. So compute, if we wanted to do appropriate level of confidence here, since this is a one-tailed test, alpha goes in the upper tail. So we also have to put the same alpha, the 0.05, in the lower tail, which would give us a 90% confidence for a confidence interval. So our confidence interval would be 90%, would be from 55.497 to 63.103. Notice 45 is not in that interval. So this confirms or reaffirms that, yes, the value of this sample does appear to be greater than 45, legitimately greater than 45. So that supports our conclusion to reject HO. A growing concern of employers is time spent on activities like surfing the internet and emailing friends during work hours. The San Luis Obispo Tribune summarized the findings of a large survey of workers in an article that ran under the headline, "Who goofs off more than 2 hours a day?" Most workers surveyed. This was on August 3rd of 2006. Suppose that the CEO of a large company wants to determine whether the average amount of wasted time during an 8-hour day for employees of her company is less than the reported 120 minutes. So that means the alternative is going to be less than. Each person in a random sample of 10 employees was contacted and asked about daily wasted time. The resulting data is shown. So those are from the 10 people. Now there's not a population standard deviation given here, so we're going to use the sample. Now since the sample size is less than 30, we need to know that it's approximately normal. Our hypotheses, we said the alternative is going to be less than the 2 hours or less than 120 minutes. Verify our assumptions. One, it was a random sample, but we need to know, since the sample size is smaller than 30, that it was approximately normal. So now this one again, boy, it's skewed in the center there, but the tails again, if this were the longer tail to go with the larger size box, I'd say it's skewed, but it's not huge. It's some skewness, but there's no huge outliers on either end. So we're going to say that it is plausible that this is normally distributed. So let's find our test statistic. Test statistic is a negative 1.07. So it appears to be smaller. Negative means it's smaller than the hypothesized mean. But is it significantly smaller? Well, the p-value, since this is less than, is going to be the probability that t is less than negative 1.07. That comes out to be a 0.15. Now, if alpha of 0.05, that is not less than alpha. So since it's greater than alpha, we failed to reject HO. So there is not sufficient evidence to conclude the mean daily wasted time for this company is less than the 120-minute standard. So we failed to reject it. It is possible that it should have been rejected. This could possibly be a type 2 error. So the power of a test and the probability of a type 2 error. Now we've got this table here that showed us where our errors occurred. Being correct, the probability that we are correct is called the power of a test. So again, looking at the student body president and the university is interested in studying the amount of money students spend on textbooks in a semester. Director of Financial Aid Services believes that the average amount spent on textbooks is $500 a semester, and uses this to determine the amount of financial aid for which a student is eligible. Student body president plans to ask each student in a random sample how much they spent on books this semester and use that data. So, of course, the student body president probably wants to show that it's more than the 500. So the alternative is greater than 500. So the null is equal to 500. And so the true mean, the null hypothesis is stating that the true mean is $500. So that's that orange curve. That's what we're assuming to be the distribution of the population. But if the true mean is only a little bit greater, let's say the true mean is really 505, this test is not going to catch that. the sample mean might look like it's bigger than 500, but it's not enough to convince us to reject. So this test is not powerful enough to pick up that small difference. If the true mean were 525, well, then it is much more likely that we would take a sample that's going to give us a large value, and we would reject that null hypothesis, reject the $500 mean. So that's the test is more likely to reject at that point. So that's what the power is describing, is how much greater does the test value have to, or the true value have to be than our hypothesized value before the test will pick it up. So the power of a test depends on the true value of the mean, which means we can never actually know what it is because we don't know the true value of the mean. If we did, we would have no reason to do a hypothesis test. So we can never actually know the power, but we can gain some insight into the power by looking at some scenarios. Let's consider a one-sided upper tail test. This is where we reject HO if our sample value is larger than that. So that means we draw our curve in, our shifted curve in like that. This is the power of the test, is 1 minus beta. However, we have no idea what beta is. The probability of committing a type 1 error, of course, is just alpha, 0.05. If the mean equals 500 is true, for what values of the sample mean would you reject the null hypothesis? Well, all the way up to that being 0.05. So you can find that value there by doing an inverse normal calculation. The value of x bar that corresponds to that cutoff point, we could take that z critical with 95.95 area to the left and get 1.645. And we can work this equation backwards to find the value of that x bar. That'd be $513.98. So if we get a sample mean of more than $513.98, we're going to reject HO here. So suppose we got standard deviation of 85. We already got that. So now if the null hypothesis is false, then mu is greater than 500. The mean is greater than 500. So now the question is, what if it is 520? That's just slightly less than that rejection, that borderline value, critical value. Well, beta is this whole probability here. That's a huge beta, which means I have a very low-powered test. We could find the probability of being less than negative, z being less than negative 0.708 in our tables if we wanted to, but it's a pretty healthy size probability. So we get 0.239. So the power then is 1 minus beta, or 0.761. So the larger the beta is, the lower our power is. Larger beta, of course, is smaller alpha. So we can use, if we can stand the tolerance, that risk of being incorrect, or the risk of incorrectly rejecting our null hypothesis. If we can stand that extra risk, using the larger alpha will significantly increase the power of the test. So if we reject HO, then the mean is greater than 500. What if it were 530? Well, here, 530, the curve would be significantly further to the right. So beta is just this probability down here, significantly smaller. Smaller beta, though, is a larger power. The power depends on the real value of the mean. The further the mean is away from our hypothesized value, the more powerful the test is. But we can never actually know what that amount is. And of course, if the hypothesized value, the true value is actually less than that critical value, then our power is extremely small. So I'm going to leave the rest of that for you guys to look over, because power is not just a huge, tool in the lower level statistics. If we're getting into advanced level statistics, actuarial statistics, it becomes a big deal. But for our purposes, we're never going to get to the point where we're looking at really finding a better estimate of that population value so that we can calculate a true power. So the factors that are the power of the test, the larger the size of the discrepancy between the hypothesized value and the true value, the higher the power is. But we don't know that. The larger the significance level is, the higher the power will be. So use the larger alpha. That's the one thing we can control. And the larger the sample size is, generally the higher the power will be. So take the largest sample that is practical to do. Okay, we're going to end it right there. That is all the material. We don't need the beta curves here or anything like that. That is all the material for this chapter. So we're going to end it there. That's our hypothesis testing. If you have any questions, let me know. Otherwise, good luck on everything.